4 astronauts orbit the Moon during what should have been a routine observation pass. Their instruments are stable, data streams without interruption. Every parameter remains within expected limits. Then, without warning, mission control falls silent for 11 seconds. Not because of a system failure, not because of signal loss, but because of what appears on the lunar surface. Silence, in this context, is not empty. It is filled with recognition. Experienced engineers and scientists do not pause without reason. They pause when something does not fit. For more than half a century, the Moon has been treated as a solved subject. A quiet, inactive body. A place where change belongs to the distant past, not the present. Its surface, marked by craters and ancient lava plains, has been understood as a record rather than an active system. This understanding was not casual. It was built on decades of observation, measurement, and verification. When scientists describe the Moon as geologically dead, they are making a precise claim. It means no ongoing internal processes strong enough to reshape the surface, no meaningful heat flow, no active transformation. Now consider the weight of that 11-second silence. It suggests that something observed does not belong within that framework. Let me clarify this carefully. Science does not change because of a single moment. It changes when evidence consistently resists explanation. But every shift begins somewhere, often with a small inconsistency that refuses to be ignored. Think of it like a clock you have trusted for years. If it suddenly skips a second, you do not discard it immediately. You watch it more closely. You test it. You ask whether the system you trusted is still complete. That is precisely where we begin, because before any theory can be challenged, it must first be clearly understood. And to understand why this moment matters, we must examine the foundation on which our knowledge of the Moon was built. To understand why that moment carries such weight, we must look carefully at how our current model of the Moon was built. Between 1969 and 1972, 12 astronauts walked across the lunar surface. Over the course of 6 missions, they collected and returned 382 kilograms of rock and soil to Earth. These were not random samples. They were selected from different regions, depths, and geological contexts, allowing scientists to reconstruct a timeline of the Moon's history with considerable precision. When these samples were analyzed in laboratories across the world, a consistent picture emerged. The Moon formed approximately 4.5 billion years ago, during a violent collision between the early Earth and a Mars-sized body known as Theia. The debris from that impact eventually coalesced into the Moon we see today. This origin explains several key properties. For example, the Moon's composition closely resembles Earth's outer layers, not its core. That is a direct consequence of the material thrown outward during the collision. In its early stages, the Moon was not quiet at all. It was partially molten, with widespread volcanic activity shaping its surface. Large basalt plains, known as maria, formed as lava cooled and solidified. Over time, however, the internal heat that drove this activity began to dissipate. Here is an important teaching point. Smaller bodies lose heat faster than larger ones. The Moon, being much smaller than Earth, could not sustain long-term internal activity. Its heat escaped into space, gradually shutting down volcanic processes. By around 3 billion years ago, this cooling reached a critical point. Volcanic activity ceased. Internal motion slowed dramatically. The Moon entered what we describe as a geologically inactive state. This conclusion was not based on assumption alone. It was supported by radiometric dating, seismic measurements from Apollo instruments, and orbital observations conducted over decades. Each method, independent of the others, reinforced the same conclusion. As a result, the Moon became one of the most well-understood bodies in planetary science, not because it was simple, but because its processes had effectively stopped. And this is the key idea we must carry forward. Our entire understanding depends on one underlying assumption. Nothing significant is changing anymore. It is precisely this assumption that will soon be tested. It is within this assumption of stability that the Artemis missions were conceived, not to discover a changing Moon, but to operate within a system believed to be largely predictable. In 2022, Artemis 1 completed an uncrewed orbital mission around the Moon. Its purpose was technical validation. Navigation systems, propulsion, thermal control, and communication were tested under real conditions. The results confirmed that a new generation of spacecraft could reliably operate in deep space. This success led directly to Artemis 2, the first crewed mission in the program. 4 astronauts were assigned, not as explorers of the unknown in the traditional sense, but as observers and preparatory agents. Their role was methodical: survey the surface, verify conditions, and gather data to support future landings. There is a useful distinction to understand here. Exploration can be divided into discovery and confirmation. Artemis 2 was designed primarily for confirmation. It assumed that the major unknowns had already been resolved by previous missions and decades of orbital mapping. By the 6th day of the mission, operations had settled into routine. The spacecraft followed a planned trajectory, passing over regions that had been imaged many times before. Instruments recorded surface composition, temperature variations, and topographical detail with high precision. The observation pass near the lunar South Pole was scheduled, not exceptional. This region is of interest because of permanently shadowed craters and the potential presence of water ice, but it was not expected to reveal anything structurally new. Everything, at least initially, aligned with expectation. Data streams were consistent. Imaging systems returned clear, stable results. There were no anomalies in spacecraft performance or environmental readings, and this is precisely what makes the next moment significant. When a system behaves exactly as predicted, any deviation becomes immediately visible. A useful analogy is a well-calibrated instrument in a laboratory. When it produces an unexpected reading, the first question is not what was discovered, but whether the instrument is at fault. Only after verification do we consider that the environment itself may be different. In this case, the instruments were functioning correctly, which leaves only one possibility. The observation itself did not match any existing prediction, and it is here that the mission begins to shift from confirmation toward discovery. It is at this precise point that observation gives way to contradiction. The data returning from the spacecraft did not simply show variation. It revealed something that should not have been there at all. Orion's imaging systems identified a surface structure measuring approximately 4.3 kilometers across. To understand the scale, consider this. It is large enough to be clearly resolved by orbital instruments, and significant enough that it should have been catalogued long ago. And yet, it was not present in existing lunar maps. This absence is not a minor oversight. Since 2009, the Lunar Reconnaissance Orbiter has been systematically mapping the Moon at high resolution. Its database includes craters, ridges, fault lines, and even relatively small surface variations. The Moon, in this sense, is one of the most thoroughly documented surfaces in the solar system. So when a feature of this size appears unrecorded, the immediate response is not excitement, but verification. Scientists cross-check data sets. They compare current images with archival records. They examine whether lighting conditions, viewing angles, or instrument artifacts could create a false impression. This process is essential. In planetary science, apparent anomalies often dissolve under closer inspection. Shadows shift. Angles distort perception. What looks new can sometimes be a reinterpretation of what was already there. But in this case, the verification process led to a more complex conclusion. The structure did exist in older data. This is where the problem deepens. It was not missing because it had never been seen. It was missing because it did not match its earlier form. The geometry, boundaries, or surface expression had changed enough that it was not immediately recognized as the same feature. Let me clarify why this matters. On Earth, surface changes are expected. Erosion, tectonic movement, and atmospheric effects constantly reshape the landscape. But the Moon lacks these active systems. Its surface is exposed, stable, and slow to evolve. A useful comparison is a footprint in dry dust. Without wind or disturbance, it can remain unchanged for an extremely long time. The lunar surface behaves in a similar way, preserving features for millions, even billions of years. So when a structure of this scale shows measurable change, the question is unavoidable. What process is capable of altering it? Because on the Moon, such changes are not expected, and when expectation fails, explanation must follow. If a structure has changed, then something must be driving that change. The next step, therefore, is not visual analysis, but measurement of energy. Thermal data provides one of the most direct ways to detect active processes. Unlike visible light, which shows shape and texture, thermal imaging reveals how heat is distributed and how it evolves over time. It answers a simple but critical question: is energy being generated, transferred, or lost? In this case, the measurements were unambiguous. The region surrounding the structure had warmed, not suddenly, but gradually. The increase was measurable, consistent across multiple passes, and confirmed by independent instruments. This is where the problem becomes more fundamental. According to the established model, the Moon should not produce internal heat that is detectable at the surface. Its interior, having cooled over billions of years, lacks the energy required to sustain such activity. Let us examine the known sources of heat. Radioactive decay does occur within the Moon's interior, but at levels far too low to produce localized surface warming of this kind. Tidal forces, caused by Earth's gravitational pull, do generate some internal stress, but again, the effect is minimal compared to what is being observed. Here is a useful teaching insight. In planetary science, when all known mechanisms fail to explain an observation, we do not discard the observation. We re-examine the system. Either a known process is being underestimated, or an unknown process is at work. Consider a simple example. If you place your hand near a surface that feels warm, you instinctively look for a heat source. If none is visible, you do not conclude that the warmth is imaginary. You conclude that the source is hidden. The same logic applies here. The measured warming implies a source of energy beneath the surface. And importantly, this is not a single reading or a transient fluctuation. The pattern persists over time. It follows a trend, not a spike. This distinction matters. Random noise can create brief anomalies. Sustained change indicates an underlying process. So, we are left with a precise and unavoidable conclusion. There is heat being generated or transferred within this region of the Moon. And heat, in any planetary body, is rarely passive. It drives movement, alters materials, and reshapes structures. In other words, it implies activity. Which brings us to the next question. If energy is present, how is it being organized? The most immediate question is simple and unavoidable. What are we actually looking at? If heat is present and sustained, it rarely remains without influence. Energy, especially within a confined environment, tends to shape the materials around it. This brings us back to the visual data, but now with a more specific question in mind. What kind of structure, if any, is emerging from this activity? The images captured by Orion do not simply show variation, they reveal organization. Within the region, there are patterns that repeat with noticeable consistency. These are not the irregular outlines of impact craters or the fractured lines of surface stress. Instead, they display angular boundaries, aligned orientations, and proportional relationships. To understand why this matters, consider how natural surfaces typically behave. On the Moon, impacts dominate. Each collision produces a crater shaped by speed, angle, and material composition. The result is diversity, not uniformity. Even when multiple craters overlap, they do not arrange themselves into consistent geometric forms. Here, however, the situation is different. Certain features appear to follow similar angles. Lines extend in parallel directions. Shapes recur in a way that suggests repetition rather than randomness. Let me offer a simple comparison. Imagine scattering pebbles across a flat surface. The arrangement will be uneven, without clear order. Now imagine placing those same pebbles in rows. The material is unchanged, but the pattern reveals intent or constraint. In scientific terms, it reflects an underlying rule. This does not imply a specific cause. It does, however, narrow the possibilities. When geometry appears in natural systems, it is usually driven by consistent forces acting over time. Crystallization, for example, produces repeating structures because atoms arrange themselves in stable configurations. But such processes require particular conditions, and they rarely operate at the scale observed here. Another important clarification is necessary. A single geometric feature can occur by chance, but a network of such features, sharing orientation and proportion, suggests that chance alone is unlikely. So we now have three linked observations: a surface feature that has changed, a measurable increase in heat, and within the same region, a pattern that appears organized rather than random. When independent observations begin to align, they shift from curiosity to evidence. The next step is to determine whether this organization is limited to the surface or whether it reflects a deeper structure beneath it. If the structure we observe on the surface is not isolated, then we must ask a deeper question. Is there a corresponding structure beneath it, guiding what we see above? To approach this, scientists turned not to images, but to seismic data. Unlike visual observation, seismic measurements allow us to infer what lies below the surface by studying how energy moves through a body. The Moon, despite being considered inactive, is not entirely silent. It experiences what we call moonquakes. These are small, often deep seismic events caused by internal stresses, temperature variations, and gravitational interactions with Earth. Now, here is where the analysis becomes particularly revealing. Historical seismic records, including data collected during the Apollo missions, were re-examined with a specific focus on the region in question. What emerged was not a random distribution of seismic activity. Instead, deep moonquakes appeared to cluster along a defined, curved line beneath the anomaly. This pattern is significant. In most natural systems, especially those without active tectonics, seismic events tend to scatter unless influenced by an underlying structure. When they align, it suggests that stress is being guided along a specific pathway. A useful way to understand this is to think of cracks forming in a material under pressure. They do not appear randomly across the entire surface. They follow lines of weakness, often extending and connecting into larger networks. In this case, the alignment of moonquakes implies that the Moon's interior, at least in this region, is not uniform. There is a structure influencing how stress is distributed and released. Let us add this to what we already know. A surface feature has changed. Heat is present beneath it. Geometric patterns suggest organization. And now, seismic activity aligns along a subsurface path directly below the same region. At this point, the observations are no longer independent. They begin to reinforce one another. Another teaching insight is important here. When multiple data sets, visual, thermal, and seismic, point toward the same location and reveal compatible patterns, the likelihood of coincidence decreases significantly. This does not yet explain the mechanism, but it does establish something more fundamental. There is structure beneath the surface, and that structure is influencing both energy and form. Which leads us to the next critical question. If heat is moving through this pathway, what else might be moving with it? If a pathway exists beneath the surface, and if heat is moving through it, then it is reasonable to ask whether that movement carries more than energy alone. In planetary systems, heat often acts as a driver, but it rarely acts in isolation. The next set of observations comes from a different type of instrument entirely, a mass spectrometer designed to detect and analyze the composition of particles in the surrounding environment, recorded an unexpected signal above the same region. Water vapor. Not in trace amounts and not evenly distributed. The concentration was significantly higher than in surrounding areas, forming a localized pattern that directly corresponds to the underlying anomaly. To understand the significance, we must consider the conditions on the lunar surface. Temperatures in shadowed regions can remain extremely low, often far below the threshold required for ice to transition into vapor. In most cases, water on the Moon is expected to remain stable as ice, particularly in permanently shaded craters. So when vapor is detected, the immediate question is not whether water exists, but how it has entered the gaseous state. Let us approach this logically. For ice to become vapor, energy must be supplied. This energy can come from sunlight, impact events, or internal heat. In this region, sunlight is insufficient, and there is no evidence of recent impacts capable of producing such a sustained effect. This leaves one remaining explanation. The water is being heated from below. Here is an important teaching insight. When a liquid or volatile substance is heated beneath a surface, It tends to migrate upward through available pathways. This is a fundamental process observed on Earth in geothermal regions, where underground heat drives the movement of water and gases toward the surface. The same principle appears to apply here. The detected vapor suggests that water, likely in the form of subsurface ice, is being converted and released through the structural pathway previously identified. This aligns with what we call hydrothermal activity. It does not require a fully molten interior, but it does require a combination of heat, material, and pathways for movement. Now consider how the pieces connect. A subsurface structure guides stress and possibly heat. That heat interacts with material below the surface, and as a result, water vapor emerges above the same region. This is no longer a single anomaly, it is a sequence of linked processes. And where processes begin to interact, systems begin to form, which leads us to the next and most important step. How do these independent observations fit together as a whole? Let us examine them with precision. First, there is a surface structure that has measurably changed over time. Second, there is a localized thermal anomaly, indicating a sustained source of heat beneath the surface. Third, seismic data reveals a defined pathway, suggesting an organized internal structure. And fourth, water vapor is being released above the same region, implying material movement driven by that heat. Individually, each of these findings would be significant. Each would require careful investigation and cautious interpretation. But science rarely advances through isolated facts. It advances when separate lines of evidence begin to converge. Here, the convergence is difficult to ignore. A useful way to understand this is to think in terms of systems rather than events. An event is a single occurrence, often temporary and self-contained. A system, by contrast, involves interaction. It has components that influence one another, producing outcomes that cannot be explained in isolation. What we are observing on the Moon fits this second category. The heat source is not simply present, it appears to be driving change. The structural pathway is not passive, it is guiding movement. The surface feature is not static, it is responding to these internal processes. And the release of water vapor is not random, it is aligned with the same underlying mechanism. This interaction suggests a process that operates over time. Heat moves through the interior. Material responds to that heat. Pressure builds, pathways open or expand, and substances migrate toward the surface. As they do, the surface itself is altered. Another teaching insight is important here. When multiple independent measurements, visual, thermal, seismic, and chemical, all point toward the same explanation, the confidence in that explanation increases significantly, not because it is proven, but because it consistently accounts for the data. So, we arrive at a critical shift in understanding. The Moon, at least in this region, is not behaving as a completely inactive body. It is exhibiting characteristics of an active geological system. This does not mean the entire Moon is changing. It means that the model we relied upon is incomplete. And when a model is incomplete, the responsibility of science is clear. It must be revised. Which leads us to the final question. If this system exists, what does it imply about the Moon as a whole? Let us examine them with precision. First, there is a surface structure that has measurably changed over time. Second, there is a localized thermal anomaly, indicating a sustained source of heat beneath the surface. Third, seismic data reveals a defined pathway, suggesting an organized internal structure. And fourth, water vapor is being released above the same region, implying material movement driven by that heat. Individually, each of these findings would be significant. Each would require careful investigation and cautious interpretation. But science rarely advances through isolated facts. It advances when separate lines of evidence begin to converge. Here, the convergence is difficult to ignore. A useful way to understand this is to think in terms of systems rather than events. An event is a single occurrence, often temporary and self-contained. A system, by contrast, involves interaction. It has components that influence one another, producing outcomes that cannot be explained in isolation. What we are observing on the Moon fits this second category. The heat source is not simply present, it appears to be driving change. The structural pathway is not passive, it is guiding movement. The surface feature is not static, it is responding to these internal processes. and the release of water vapor is not random. It is aligned with the same underlying mechanism. This interaction suggests a process that operates over time. Heat moves through the interior. Material responds to that heat. Pressure builds, pathways open or expand, and substances migrate toward the surface. As they do, the surface itself is altered. Another teaching insight is important here. When multiple independent measurements, visual, thermal, seismic, and chemical, all point toward the same explanation, the confidence in that explanation increases significantly, not because it is proven, but because it consistently accounts for the data. So we arrive at a critical shift in understanding. The Moon, at least in this region, is not behaving as a completely inactive body. It is exhibiting characteristics of an active geological system. This does not mean the entire Moon is changing. It means that the model we relied upon is incomplete. And when a model is incomplete, the responsibility of science is clear. It must be revised. Which leads us to the final question. If this system exists, what does it imply about the Moon as a whole?